In our previous session, we have discussed the types of wings, position of wings, and the parts of wing structure of RC plane. Now we will start off with the RC airfoil design and how it is linked to the wing of aircraft. The forward section of the airfoil is named as the leading edge and the rear the trailing edge. The airfoil upper and lower surfaces meet at the leading and trailing edge. The length of the airfoil from leading to trailing edge is known as the airfoil chord. This often varies down the span of the wing as the wing tapers from the root to tip. The thickness of the airfoil is a very important design parameter and is always expressed as the percentage of the total chord. The design parameter, camber, is a measure of a symmetry between the upper and lower surface. Camber is generally introduced to an airfoil to increase its maximum lift coefficient, which in turn decreases the stall speed of the aircraft. Highly cambered airfoils produce more lift than less cambered airfoil, and an airfoil that has no camber is called symmetrical. The angle of attack is the angle at which the relative wind meets an airfoil. It is the angle formed by the chord line of the airfoil and the direction of the relative wind, or the vector representing the relative motion between the aircraft and the atmosphere. There are different types of airfoil: flat bottom, semi-symmetrical, symmetrical, undercambered, and flat. Just remember, symmetrical airfoil has identical upper and lower surfaces such that the chord line and mean camber line are the same, producing no lift at zero angle of attack. Non-symmetrical airfoil, also known as cambered airfoil, has different upper and lower surface such that the chord line is placed above the large curvature. These have different chord line and camber line. The advantage of non-symmetrical airfoil is that lift-to-drag ratio and stall characteristics are better and useful lift is produced at zero angle of attack. You can read further on airfoil aerodynamics if interested in the link given below. An airfoil is constructed in such a way that its shape takes advantage of the air's response to certain physical laws. This develops two actions from the air mass: a positive pressure lifting action from the air mass below the wing and the negative pressure lifting action from lowered pressure above the wing. This theory can be labeled as longer path theory or equal transit time theory. The theory states that airfoils are shaped with the upper surface longer than the bottom. The air molecules have further to travel over the top of the airfoil than along the bottom. In order to meet up at the trailing edge, the molecules going over the top of the wing must travel faster than the molecule going under the wing. Because the upper flow is faster, the pressure is lower. The difference in pressure across the airfoil produces lift. The pressure differential created between the upper and the lower surface of the wing lifts the wing upward in the direction of lowered pressure. This lifting force is known as induced lift. Induced lift may be increased within limits by increasing the angle of attack of the wing, or changing the shape of the airfoil, changing the geometry, that is the aspect ratio, or by increasing the wing area, or increasing the free stream velocity, or by change in air density. Let us move on and compare in details the difference between the symmetrical NACA 0012 and unsymmetrical NACA 2412 airfoil. As the airflow velocity increases along the surface of the wing, the pressure along the surface of the wing decreases. Similarly, an increase in angle of attack will increase the separation between the airfoil's upper and lower section coefficient of pressure. In the same way, the aeroplane wings get more lift as it increases its angle of attack. The NACA 2412 airfoil receives drastically more pressure loss as the angle of attack increases, producing a strong lifting force. Let us see how to read a pressure distribution curve. The upper surface pressure is lower, plotted higher on the usual scale than the lower surface, represented as Cp, but it does not have to be lower surface. The lower surface sometimes carries a positive pressure, but at times design condition is usually pulling the wing downward. In this case, some suction, that is negative Cp, downward force on lower surface is present under the midchord. Pressure recovery. This region of the pressure distribution is called the pressure recovery region. The pressure increases from its minimum value to the value at the trailing edge. This area is also known as region of adverse pressure gradient. As discussed in the other sessions, the adverse pressure gradient is associated with boundary layer transition and simply separation if the gradient is too severe. Trailing pressure. The pressure at the trailing edge is related to the airfoil thickness and shape near the trailing edge. For thick airfoils, the pressure here is slightly positive. The velocity is a bit less than free stream velocity. For infinitely thin section, Cp is equals to 0 at the trailing edge. Large positive values of Cp at the trailing edge implies more severe adverse pressure gradient. Stagnation point occurs near the leading edge. It is a place at which velocity is equals to 0. Note that in incompressible flow, Cp is equals to 1.0 at this point. Hence, from the reading, we get coefficient of lift is equals to 1.0548 for NACA 0012 and coefficient of lift is equals to 1.2378 for NACA 2412, by which we can conclude that cambered airfoils give better lift than symmetrical airfoils. Let's get into what is that we call NACA series. The NACA 4-digit wing section defines the profile shown here. First digit describing the maximum camber as percentage of chord, second digit describing the distance of maximum camber from the airfoil leading edge in tenths of the chord, last two digit describing the maximum thickness of the airfoil as a percentage of chord. Let us look into an example. NACA 0012. The NACA 0012 airfoil is symmetrical. The 00 indicates that it has no camber. The 12 indicates that the airfoil has a 12% thickness to chord length ratio. It is 12% as thick as it is long. In the graph, it shows coefficient of lift increases linearly at small angle of attack till it reaches the stall angle. Thereafter, there is a sudden loss of lift. This behavior is seen in the plot as well. The stall angle is at 13 degrees. The drag is low for low angle of attack as expected and increases at a faster rate with increasing angle of attack. Let us look into another example. NACA 2412 airfoil has maximum camber of 2% located at 40% from the leading edge with a maximum thickness of 12% of the chord. In the graph, it shows coefficient of lift increases linearly at small angle of attack but produces more lift at 0 degree angle of attack till it reaches the stall angle. Thereafter, there is a sudden loss of lift. This behavior is seen in the plot as well. The stall angle is after 14 degrees here. The lift coefficient versus angle of attack characteristics of airfoil is shown here. This is NACA 0012. And this is NACA 2412, coefficient of lift versus alpha curve for three different Reynolds in their increasing order. At all Reynolds number, the lift coefficient for the airfoil also increases. As Reynolds number decreases, the lift coefficient also decreases. A large difference in the pressure coefficient is observed between the top and the bottom surface in case of the lower Reynolds number, and thus it indicates that at low Reynolds number, high lift is generated than at high Reynolds number. Another thing that we can notice here is that cambered 2412 airfoil produces lift at less than 0 degree angle of attack than the symmetrical 0012 airfoil. Now, from the understanding of wing and airfoil design, we can conclude that rectangular wing is found mostly on small aircraft with NACA 2412 airfoil. It produces good lift at low speed. It produces good and stable flight. It is cheap and can be made lighter. Green lines represent the lift of the aircraft, whereas the yellow lines represent the drag of the aircraft. This table here shows the list produced by 0012 and 2412 airfoil as the dimension of wingspan and wing chord changes. At constant chord, as wingspan increases, the lift of the wing also increases. At constant span, as wing chord increases, the lift of the wing also increases. The NACA 0012 undergoes stall at 0.220 meter chord, hence no lift, whereas 2412 still produces lift. But in either ways, the lift produced by 2412 is always better than 0012 NACA series. This is just to make you understand how cambered airfoils are better than symmetrical airfoils. I hope you guys would have understood today's session. Let us move on to motion of flight and thrust calculations in the next session. Thank you.